Hi, my name is JHarmon. I'm taking all three of the classes and I'll be talking about the power management system for KI1. So you'll see the system on the screen. There is two halves to it, one being the full wave rectifier and the other being the RC circuit. So on the full wave rectifier, if we were to zoom in on one of the diodes, we would see charge buildup. On the P-type side, we're going to see negative charge, and on the N-type side, we're going to see positive charge. This creates a potential difference across the diode and therefore an electric field through the depletion region. This inbuilt potential is the threshold voltage, and this is what helps determine what sort of mode the diode is going to be in. If the voltage across the diode is less than the threshold voltage, the electric field in the depletion region is going to prevent current from flowing, and if it's greater than or equal to, the diode is going to begin to turn on. In the case of the full wave rectifier, when the rectifier itself is on, there needs to be two diodes on, and those will be in series. So at minimum, the source, in order for the rectifier to be on, will need to have at least a difference of twice the threshold voltage. So first, where exactly does this threshold voltage come from? So if we look at a PN junction, we would see that there is a equal and opposite charge density on either half. And taking the differential form of Gauss's law, we would be able to calculate the electric field in the diode, and then from that, through integration, we'd be able to acquire the voltage. And from the values at the far ends of the diode, so on the far side of the P-type side, we would get a value of negative V0, which would just be a constant, and then on the right side, we would also get a value of positive V0. So in total, the difference across the diode is going to be 2 V0, and that's the value of the voltage as threshold, or VD on. And so if the threshold value is higher, obviously the electric field in the depletion region is also going to be higher. This means that the work that needs to be done against the field is going to increase, and that manifests itself in a couple of ways. So we'll see in the amplitude of the rectifier output is going to be decreased by twice VD on, and then we're also going to be seeing a delay from when the source turns on to when the rectifier is producing an output. And this is because the source is increasing its voltage, but it hasn't met the twice VD on level, so the output is still 0. Now for the output signal of the rectifier is obviously the input signal to the RC circuit. So it's important to know whether that rectifier system is linear and time invariant. So in order to test time invariance, we can see that there's no changing in the values in the rectifier, and obviously a delay in the input signal is going to cause a corresponding delay in the output signal. But as for linearity, it's an if and only if property, meaning to disprove linearity of a system, we only need to disprove one of those elements. So the easiest way to see that the system is not linear is to test homogeneity, and if we were to take a signal x of t and it produces a certain output, and then we were to take a second output which is x of t times a constant -1, we would expect to see the output would be the same -1 times the original output, but what we see is an identical output to the first output, meaning that homogeneity is not satisfied, so the entire system is not linear. Because it's time invariant, we see that a periodic input is also going to produce a periodic output, which is important considering for an AC to DC converter, the input's obviously going to be periodic. Now for the RC circuit, there's only one capacitor, which means that it follows a first order differential equation. Acquiring this differential equation with the solution y of t will allow us to test whether the system itself is linear. So by substituting in for y of t, a second y of t, which would be a constant coefficient times y of t plus a second coefficient times another y of t, and solving for that, we see that the solution is in terms of the original y of t solution. Therefore, the system is linear. And again, time invariance, we can see this just through observation. None of the circuit components are changing with time, and a delay in the input of the signal is going to produce an identical delay in the output of the RC circuit. So the point of the RC circuit here is to smooth the output of the rectifier. And this is done by the capacitor reducing the change in voltage over time of that output. We can see this behavior by observation. At time equals 0, the capacitor is going to have 0 voltage across it, and at time infinity, time steady state, we're going to see that the voltage reaches a maximum. In between, there's going to be an exponential characteristic that follows the time constant of the system, and that's just going to be the equivalent resistance of the capacitor at the capacitor and the capacitance of the capacitor itself. So for the system output, we're going to see that the voltage of the rectifier is going to be the voltage in minus twice VD on again, and the voltage out of the total output is going to be the voltage of the rectifier minus the voltage across the resistor 1. So as a capacitor, it starts to charge. The voltage begins to match the source, which in this case would be the voltage of the rectifier. Eventually, that means that the difference between the rectifier output and the voltage output of the entire system is going to be 0. This means that the current through resistor 1 is also going to be 0, which means that this system is turned off. However, the capacitor is still just discharging through resistor 2, and this is what causes the smoothing factor. The decay that happens in between the periods of the voltage of the rectifier can be modeled as a linear approximation, and this is just gained through a truncation of the Taylor series. So in summary, the internals of the system, such as the voltage threshold of the diode, the response of the capacitor, combine to form a nonlinear yet time invariant system which converts an AC signal to DC for use by a device. Thanks.